So thank you very much. I'm very happy to be here, even if in virtual situation. I thank the organizers for this conference, for having organized it in a very short time. And all right, so I'm very happy to see many friends, even online, but that's what is possible for now. So I will be talking about some class of degenerate partial differential equations, and I will be concerned on solvability of such a class. So I want to say that this is joint work with Serena Federico. And let me just outline if I can, yeah. All right, so here is the outline of my talk. And I just want to say that solvability of PDEs is completely open, okay? Even though the Nuremberg-Travers conjecture was settled recently, relatively recently, by Niels Denker, based on work by Nicolas Lerner, there is plenty of classes of differential equations that are not under control. And the class I will be considering is a class of operators with multiple characteristics, but they are quite degenerate. And there are two sorts of degeneracies that cooperate, in a sense, and negatively maybe. And we're interested in saying, looking at situation which one can hope at least for better local solvability. Better means better than L2. So the plan is the following. First, I will give the definition of solvability, particularly HS to HS prime solvability. This will be the main solvability we'll be concerned with. And then we'll try to summarize very quickly what is known about multiple characteristics, and then talk about the starting model and discuss our model. So ST stands for Schrodinger type, MT for mixed type, and MST mixed Schrodinger type. So we'll see the corresponding, these are three different classes of operators will be considered. And then of course, in the meanwhile, we give examples, and we'll be closing by giving a few remarks. So well, okay, so local solvability means that any given point of an open set possesses some neighborhood for which, if V is infinity of omega and U is in the prime is distribution for which PU equals V in V, then this is true, okay? So given any function V, which is infinity, we may find a distribution U for which the solution is solved in this neighborhood. So this is the notion I will be mainly focusing my talk on. It's HS to HS prime local solvability near X naught. This means that given a point X naught in omega, and given S and S prime real number, we may find a compact neighborhood of X naught such that given any function HS log omega, we may find a distribution HS prime log omega, satisfying the equation over U. If we are able to do this for any given S and S prime has this form, S plus M minus R, then R would be called loss of derivatives. So, but unfortunately, our results are going to be, well, I will be giving the results when S and S prime are fixed. One has to bear in mind that solvability estimates are the main tool for obtaining local solvability. And through the use of the Hambanack theorem, the local solvability, say HS to HS prime, means that we have to find this kind of a priori estimate for any given function completely supported in K. Okay, where K is this compact which are looking for. And in passing, this is very interesting because one has to look for this kind of a priori estimates, and these are very delicate estimates. So one of the main ingredients will be the use of the Pfeffer-Maffong inequality, which is very delicate, because it goes really deeply into the structure of the operator. So what is the state of the art in the multiple characteristics? I think that there is a main first paper, and actually a number of papers by Mendoza and Ullman. They consider the operator P of this form, and then they gave a condition for which one does not have a local solvability. And it does not have local solvability if the imaginary part of Q1 changes sign on bicharacteristic of symbols C1 and C2, which are X1, X2 lines at the double points. And this is called the condition sub P, which is should be compared to the condition psi of Nirenberg and Travis, okay? And then there is also a number of papers by Corwin, Rothschild, Müller, Peloso, and Ricci, Demari, and so on. They are mainly concerned with left invariant vector fields on step 2 nilpotent groups, and they have the algebraic structure which is helping them to find out some local solvability results. More recently, Müller was considering some operators, more general, degenerate second order operators for which he gave necessary conditions. Okay, sufficient in some cases, but some cases are completely related again to step 2 nilpotent groups. Okay, so I think that's why I'm more interested in necessary conditions, and I want to recall this, which you should nevertheless, so it's a condition depending on the principal part. But since the operator is degenerate, that's not enough. So there is a gap, I mean, from having sufficient conditions also. The gap, when there is some algebra, can be filled in by, some auxiliary step 2 nilpotent structure and so on. And then there are some results by Travis for operators like P1 times P2 plus IQ1. P1 and P2 are real principal type, Q1 real. And one has, this is elliptic. I mean, the symbol, the principle, this kind of symbol is elliptic. In this case, he has a result which is a HS to HS plus 1 local solvability with the loss of one derivative. I want to mention also the previous result by Alfer. It was considered a similar operator. It was studying the loss of the apolepticity with the loss of one derivative. So this is very much, related to local solvability, because one has to remember that P star hypoelliptic imply P locally solvable. So any kind of hypoellipticity result gives result about the adjoint, local solvability result about for the adjoint. And then there is a Kanai, celebrated Kanai example, a hypoelliptic but non-solvable operator for which, Colombini, Cornaro, and Pernazza, and also later Federico and myself took the inspiration for this class of operator we are going to consider. Then let me mention also the work by J.J. Cohn about sums of squares of complex vector fields. That must be divergence free, but anyway, so, and then also some paper by myself and Cesare Parenti about semi-global solvability. These are results for multiple transversal symplectic characteristics. So these are very degenerate operators. But I'm not going to talk any further because it's here. I'm not going to recall what semi-global solvability means. And then there is some recent work by Denker about operators of a subprincipal type. In this case, one has involutive characteristic manifold, and it gives some necessary conditions. It should be also compared with some previous work by Popivanov, but a very old work by Popivanov. And then there is also the papers by Travis about real or complex vector fields with critical points, for which some local solvability results, HS to HS prime solvability results, and semi-global solvability results are still an issue. So remember, P star hypoelliptic implies P locally solvables. This means also that the hypoelliptic operator by Bills and Pfefferman, the class considered by Akamatsu, Zuili, Boutet, Grigis, and Fer, and also Parenti and Rodino, Cohn, and Parenti myself, for which you can characterize the hypoellipticity, give information about local solvability. So what is the Kanai example? So the Kanai example is actually P star. P star is an operator which is hypoelliptic and non-solvable near X1. Okay, but since it's hypoelliptic, the adjoint is solvable. So you may see here two ingredients. So here the symbol is x1 xi2 squared. This means that this operator xi2 squared is a Laplacian in the x2 variable, so it's degenerate. And then you have x1. x1 is an extra degeneracy, okay? But then there is this vector field here is going to rescue the situation for solvability. So building on this example, Colombini, Cordaro, and Pernazza considered this operator here. We have a vector field. Actually, I'm going to call vector field something which is described using the capital D derivatives. That means the complex derivatives, okay? But you are going to forgive me about that. So you take an operator for x star fx plus ix naught plus some function, complex, whatever. And they consider the case when f is analytic and x naught is never zero, and which is transversal, well, where f changes sign. So this is in the suitable sense, because f, although it's analytic, has a very complicated set of vanishing. And the result is that f naught is zero, okay, so you have some place where you have a zero, and you have that ix naught is against the sign of the function f is non-negative, which is called by them the small psi condition. Then you may have L2 to L2 local solvability near zero. So they establish the a priori estimate in L2 in a neighborhood of zero. So the point, you see, here you have only one vector field, so this is very much an involutive situation. So x commutes with itself, so there is no extra situation, because then ix naught is completely taken by this condition here. And so this is, in a sense, very, very roughly speaking, gives you this kind of solvability. But then the question is, can we hope for better regularity? So with Serena, we considered these three kinds of operators. In this first case, you see, here we have a sandwich of the function f, we have a vector fields like before, and then we have here something which is complex in a sense, okay? It has some first order part, which is complex. So these are operators that must be real with real principal symbols, in this case, in the case MT, then also in MST. So in the mixed type and mixed Schrodinger type, we have this. And then in the Schrodinger type, you see here x naught is no more there, see? So it has only capital D derivatives, real coefficient, but capital D derivatives. This means it's a Schrodinger kind of operator. Here you notice also that we have many fj, which concur to give some degeneracy. Instead, here only one. Here again, many. The point is that the zero set of f must be non-degenerate, which is the reason for this, this condition here. So in a sense, well, anyway, so let me, I'm sorry. So I have to go back here. In the MT case, we'll see that there is a characteristic set, which is given by the contempt, I mean, the vanishing, the intersection of the vanishing sets of xj and of x naught, okay? So xn plus 1 does not concur, does not give any contribution in this case.
Can I ask a question?
Yes?
What is the difference between MT and MST?
MT, MST, you see only one function here, you have many functions here. So the degeneracy may be much more.
Oh, I see, yes.
Right. But this, we're going to see this is as a kind of a perturbation of this situation here. But this is the main difference, okay? And I want to say also that our class contains operator whose formal adjoint is not hyperelliptic, okay? So it is not containing the results by Akamatsu, and it is not containing the results by Zwilly. About Akamatsu and Zwilly studied this kind of operator, hypoellipticity. But anyways, does not, so it does not exhaust our class. So what are the conditions in the mixed type, in the empty kind? You see, ix naught f must be bigger than 0. So moving along the direction of x naught, f changes sign from 0 to plus, okay? Because we must have a 0. And then we have a control of the Poisson brackets between among in general the commutator of xj and x naught must be controlled by the principal symbol of the sum of squares starting from 0. So x naught contributes to this, okay? So xn plus 1 is mute for a while. But then here it comes. Also, we must have the divergence of x naught times the vector field xn plus 1 must be again controlled by this kind of symbol. And let me just skip condition H4, which is maybe contained in condition H5. Condition H4 is a sufficient condition for having the Mellin inequality that I'm going to recall. But let me just skip this, and because in the case k equals 1, then we 2, I'm sorry, then this condition is equivalent to the H5 condition. This one is symplectical invariant, but anyway, let me just state this. So the span of these vector fields and the commutators up to length k at x, okay? And you take a point, so this is the span, all right? This is a vector space. You take all these kind of things. This is a kind of Rothschild-Stein condition. And then you have that at any point where you have a degeneracy for f, which is also a degeneracy of that characteristic set, okay? The fiber over x naught has to see some characteristic points. You may find an R such that the dimension of this vector space up to, you see, you use the vector fields x0, x1 up to xn, not xn plus 1, is not important in that case, and the commutators up to length R. And so this is going to be the tangent space then, all right? So this is a sort of Hormander condition. So once you have these conditions, you have this kind of result. We are going to focus on solvability near the problematic set where f is 0. So we have this kind of extra degeneracy, okay? So suppose H1, H2, H3. All right, so you had transversality of the flow of x naught through the 0 set with respect to the 0 set of f, and then controllability of these Poisson brackets and this vector field with respect to this the principal part. Okay, H1, H2, H3 are assumed. Then for any point which is a degenerate for f, then the operators L2 to L2 locally solvable near x naught. So although you change sign, then you may find, given any source terminal 2, well, near x naught, you may find a distribution which solves the equation there. So if x naught is in S, and of course you want to see that also there is some degeneracy given by the characteristic set, which is a 0 set of x0, x1 up to xn, and H4 holds. H4 is this kind of the Mellin condition, which is that L2 result. Then we have this result. We have solvability H minus 1/2 to L2. This means that the source term H minus 1/2, then you may find a distribution in L2 which is equal P, such that P1 U is equal to V near x naught. And then here, just more in general, we have the condition H5, the Hormander condition at step bigger than 3, say, because R equals 2 is this point over here. Well, we have solvability H minus 1R to L2, okay? So we have this kind of extra degeneracy, but nevertheless, we may find a solution, which is better in a sense. You see, I don't talk about a gain of 2 minus 1 over R derivatives, but in a sense, there is some gain. But anyway, so it's very delicate to extend this to HS, but I will remark on this at the end. And then in the end, if you have a point for which f is degenerate, but then the fiber of this point does not meet the 0 set of this characteristic set, well, then P1 is H minus 1 to L2 locally solvable near x naught. This is exactly the case of the adjoint of the Kanai operator. So you have H minus 1 to L2 local solvability. Because you see, if you take the sums of squares, take off f plus the x naught squared, then it's elliptic because you don't see microlocally elliptic, you don't see the singularity. So we have this kind of result. One may ask also what happens out of S. Well, what that does not really have to impose all these conditions. So in general, one can have L2 to L2 local solvability. But then the conditions are much weaker. So what is the point? The main estimate, well, we take this kind of energy control. You see, we take the adjoint. Of course, we want to have a a priori estimate, and then we take this kind of weight, this multiplier, so the differential multiplier, which is differential multiplier, exactly. And what we get, we have this kind of a priori control. You can see here, these are sums of squares, and then we also want to take also out of this some x naught part. And then we have some error term, which is L2, okay? And so we take a compact sufficiently small, which contains in the interior x naught. Then we can find this. So how to get this estimate? Well, one take this estimate by commuting x naught over here, and then in the end, well, things boil down to a Pfefferman-Fong inequality. So the operator we have to control, whose L2 quadratic form we have to control, is of this kind of here. You see, here's the sum of the squares. We have this kind of correction of the commutators, and then with this contribution, which is the real part of the divergence of x naught times the xn plus 1 vector. But you see, the point is the following, that since, so here there are some parameters, epsilon, where you see epsilon is an infinity norm of the function f, which is going to 0 if k goes to 0. I mean, sorry, k shrinks to the point x naught, because x naught is a vanishing point for f. So this is actually a perturbation. So the estimate, I mean, the condition, these two conditions are exactly the ones that are granting the use of the Pfefferman-Fong inequality in this case. And then we can control this thing here. Once we have this kind of control, well, you see, in the end, by taking Cauchy-Schwarz, we have this control. P star u 0 squared, L2 norm squared, is controlled from below. We take away all this thing here, but we want to be very careful with this, because you see in the Cauchy-Schwarz norm, I mean inequality, we have this kind of contribution, small constant over here, we can reabsorb by this one here. And then this is going to control this S Sobolev norm, provided we're in such a position, minus a big constant times the L2 norm of squared, which is, you see, this part here is although the contribution of this kind goes over here then, and over here. So S is equal to 1 when you have that the fiber of x naught does not intersect the characteristic set. So this is because we have the full strength of the Gordon inequality. So this part here controls this with S equals 1. Or if we have Melin's inequality, then we have a 1/2. Or in general, the Rothschild-Stein estimate gives 1 over R in general, provided we have that spanning of the vector, that vector space spanned by the vector fields and the commutations up to order R. So you can see here, from here, we are in business, because then you see, we clean up this kind of thing by using a Poincaré estimate. So since x naught is non-degenerate, this is going to be controlling also this one, provided we shrink further the compact K. And so we get our a priori estimate. This thing here controls the L2 norm of U by positive constant, and we're in business. So let me just very briefly, because the time is running away. So this is just to show you that the Beals-Pfefferman class of operators falls into this kind of normal form, say, because they assume that the coefficient function, which is appearing here, has a constant dimension in the kernel. So this is a kind of toy model, but anyway, so you can always find out the situation in which you have this kind of sums of squares. In this case, anyway, we cannot have a better regularity because we cannot really count on the Melin or the Rothschild-Stein estimate, because really this commutator is going to be a multiple of this vector field X, which is really generating the X1 and X2. So, but nevertheless, this is a very degenerate operator, which is L2 to L2 locally solvable. Here is an example. I have to be very quick, but you see here for which I want to use the Rothschild-Stein or Melin's estimate. You see, in this case, x1 is the x1, x2 is x1 to the k dx3, x3 is this kind of vector field, and x0 is 0. So x3 is a n plus first vector, x0 is our x0. So in this case, we consider this operator here. There is a zero divergence for x0, so one sees easily that everything is under control. And actually, we have that this is an operator which is h minus 1 over k plus 1, because you see the generation, of course, if you take k plus 1 commutators in this case, and k commutators, but then the gain by the Rothschild-Stein theorem is k plus 1, the best one is of this kind here, to L2 locally solvable x2 equals 0. So k is equal to 0 when the characteristic set is 0. Well, in this case, we have that the characteristic set is 0, otherwise we have the Romander condition or the Melin condition. So I wanted to stress the Melin condition because Melin's condition is a symplectical invariant, which is very interesting to extend this kind of results for more general classes of operators. So this, let me just be very quick because I think I have still 5 minutes. Am I right?
Yes.
All right. Okay. So this is very interesting to me, this example. Again, you see, we have two vector fields. F is sandwiched in here, and x3, which is the n plus first vector field, plus ix0. So x1 and x2 are these vector fields. x0 is this thing here. So we have a certain kind of generation of the Lie algebra. x3 is this vector field, should be harmless in a sense. But the point is that we may, well, you see, the point is that, I cannot see something here. All right. So you see, having f of x, this function, which is any function, but I want to take omega plus or n minus to be defined by this inequality in x1. So you see, whenever x0 belongs to the zero set of that function intersection omega plus or minus, we have h minus 1 to L2 local solvability because the fiber of these points with the characteristic set are empty. So, which is this kind of thing here. But if you take a point, which is actually in here, you see here x0 0 is minus 1. So it's really on this kind of boundary of these two different regions, this fiber intersects sigma. And in this case, we have Melin's inequality, which means that we have h minus 1/2 to L2 local solvability near x0. So what is the point of this example? The point of this example is not even over the zero set of f. We may hope for having some global gain or loss of derivatives, okay? You can see that from here, in some regions, we have h minus 1, here h minus 1/2. So the loss or gain of derivatives in this kind of very loose sense is non-constant. So this is an interesting example because of that. All right, I cannot, all right, so I should be able, all right, so let me then talk about the Schrodinger case. So here there is no ix0 vector field. So this is, since this vector field is described by considering capital D derivatives, well, we have many functions here. There is not really the need to have only one function, which is really considering this kind of extra degeneracy. So, but in this case, the vector fields x1 to xn have complex coefficients. And then we have to assume that at any point of omega, we may find a connect neighborhood of which is of x0, which is contained in omega, and a function, so infinity over there, such that the xj, g are 0. So the xj are tangent to the level sets of g. And so that this means the real part and the imaginary part of these vector fields. And then xn plus 1g is transversal. So it's going to move g, okay? So in this case, we still have a solvability regardless the zero set of the Fj. But we have L2 to L2 local solvability. The point is that considering the energy as before is really not giving you very much. So the point, there is some kind of general reason why, so it's not the use of x naught vector, I mean, there is no x naught in fact, but anyway, the xn plus 1 vector field over here as a multiplier does not help you. So this is a really something which is completely connected to the Schrodinger type, really. And so what we get, we estimate, by Karleman estimate this energy here, and we get the result. An example may be given by considering this kind of Mitsuhata structure, okay? Q are real quadratic forms, real valued, of course, you know, we have this thing here, and then we take a pair to xn plus 1 of this kind here. So in a sense, we have the g of t equal t. This means that we have a cylindric structure, Mitsuhata structure. So that all the level set of g are going to give some kind of, well, they are called hypoanalytic structure in the sense of Travis. And this may represent, this operator here represents some kind of evolution of these manifolds. So it is something that, it is not clear. Anyway, so in this case, L2 to L2. And then there is also the mixed Schrodinger type case, in which again, xj must be real, and we have many functions. And then again, we have the presence, simultaneous presence of xn plus 1 and ix naught. This case was studied by Serena herself, I mean, in a single paper by her. In this case, again, you see, ix naught should not have any critical points. And then we have a weaker condition of evolution, but of all fj. This means that if you take, it's a kind of cone condition, okay? So x naught should be pointing some, if you take the differentials of the fj, and then you take all of them, so x naught should be pointing in the interior of the cone determined by all these kind of facets, the hyperplanes. And then x naught must be commuted with xj. And then again, there is a condition of this kind. Here you see ix naught fj is non-negative. So this is a degenerate operator, but the symbol is non-negative. And again, the commutator should be controlled. And in this case, again, you have L2 to L2. So in a sense, you see, this part here is going to contribute by some kind of heat equation. And here is the Schrodinger part. The Schrodinger part still has a predominance in a sense, because it's going to ruin things. So some kind of smoothing, which might be given by this and the kind of family you're considering, is going to be ruined in a sense. So again, you consider this kind of energy, which was the energy I considered also in the previous case. And again, so the auxiliary operator here is a P naught, and that's why you have to assume those conditions to be able to apply the Pfefferman-Fong inequality to this situation here. See, the point that you really need the full strength of the Pfefferman-Fong inequality, because the zero set, the characteristic set of this operator has no nice geometric structure in general. So you cannot really use the Hormander theorem, which would be very nice, but it is too strong. In this kind of a loose situation, you want to have this thing. And very quickly, so there are also some kind of mildly complex cases in which but I decided not to talk about them because they are very mild as a complex case. So everything is reduced to the real case, and this is not so meaningful, I think. But how about solvability in HS spaces? This means that we have to commute with some micro-localizer, a lambda S operator, but the commutator is too big in general. So this is a big problem, because the operator is very degenerate. So commutators must be completely taken under control. And we know that the micro-localization for the Nirenberg-Traves conjecture was a nightmare, and is a nightmare. So this thing here is very delicate. So one would like to have, for instance, HS to HS plus 1/2 solvability. In this case, then you really can understand the loss of derivatives. But the example I showed near the zero set of F says that actually the loss of derivative may be depending on the, really on the geometry, on the location with respect to some stratification. And how about the propagation singularities? So you want to understand propagation in solvable space, I mean, in solvable spaces, in fact, because if you have this kind of result and actually want to have propagation regularity, then you may find semi-global and global solvability, which will be very interesting. And the final issue, which is very interesting to me, LP to LQ local solvability. So you take P and Q different from 2, and then you take also, to avoid some problematic situation, you take them strictly in between 1 and infinity. Can you have a priori estimates which are granting some LP to LQ local solvability? So this is very interesting because it's related to some generalization of Strickler's estimates. So that would be something one should understand also to me. And I thank you very much for your attention. I'm sorry because I think I went over by a few minutes. Okay, yeah. Thank you very much.
Thank you very much for this nice talk. Are there any questions? Okay, I have a question. So actually my question is about the Schrodinger type class that we analyzed. Mm-hmm. So I think it's interesting because in the class, yes, if you go back, please, in the class we have these degenerate Schrodinger operators, and in particular we can find operators depending on, if we consider a space-time domain, we can consider Schrodinger operators with variable coefficients depending on space, on the space variable, and which are in particular degenerate. So for these operators, we have these results about local solvability. Do you think these results can give us information about the possible local well-posedness of the linear Cauchy problem for these operators?
Yeah, I think so, but it depends on the geometry then. This I would say that, so if you want to consider some functions fj and so on, so depends, I would say that it should be depending on the positions of the fj, in a sense. Just because the concern would be that I like to, so the function g, which is here supposed to be existing, you know, does not have any.
Exactly. Interaction functions fj. So
exactly. So I would like to have that xn plus 1 should be really some evolution direction for which also the fj are well positioned. So it might be that the condition is the one that you considered here, you see? So there must be also another condition of this kind here. Because really you want to have a propagation cone somewhere.
I see.
This is what I'm thinking.
Okay, thank you very much. Any other question?
Let me just add a final remark. You see, this class is complementary in a sense to the class considered by Denker about sub-principal operators. So there is a lot of structure here, and the two things should be compared, in fact.
Thank you very much for this very nice talk. Any other question?
Can I ask Alberto just maybe, of course, very naive question for you. If we are interested in, you mentioned LP-LQ estimates, and if we are also interested in a weaker concept like global hyperellipticity, then, for example, if you take, in that case, if you take vectors xj to be constant coefficients, so then you can calculate the symbol of the whole operator, and then by using some Hermando type condition or maybe some other analysis, you can put conditions on for the invertibility of this operator. So then, what do you think?
So, but you are in the case of a bounded set, you mean, or you are on a torus, say?
No, on the whole space, for example.
Well, on the whole space, I don't really know, because you see the hypolipticity is something which is very fine depending on the complex zero set. So that would be certainly interesting, I think, even in the case you mentioned. So if you take some kind of sandwich of because you see the point is that the function f is no longer giving you constant coefficients. So,
but if the vector fields are constant coefficient, because actually I'm thinking of the case of groups, and then if the vector fields xj are constant coefficients, one can calculate the symbol, and then one can.
Yeah, but you have to. You really have. You still have to cope with the singularity given by the zeros of the function f of the many functions fj.
But yes, that's exactly the point, that you put then you see from that condition you see conditions on f which you could guarantee, for example.
But you see, the point is that in that case, this thing here is going to create some lower order terms that are not so lower order. So that's a point. So because if you want to compute that operator, then you have the xj acting over f, and so they give you some lower order part. Of course, it has zeros, so there are some Levy conditions that are respected. So, but I would say that the behavior, say at infinity of f, would matter then, because you see in this kind of global hypolipticity questions, also some localization at infinity is also important. So, but this certainly is a very interesting question. So I think it's doable in a sense. One has to work.
If I can add something, as Alberto already mentioned, there is a result about the hyperellipticity of operators of this form. So in that case, this result of Akamatsu, in this result, he considers operators with variable coefficients vector fields, but of course you can apply the result also to constant coefficients vector fields, and you have to put some conditions regarding the vector fields and the function and the interaction of this. So in the theorem, Akamatsu asks that the vector fields appearing in the second order part have to be tangent to the zero set of f, which is the function in the second order part given the degeneracy. And also you need a commutation relation between the first order part and the second order part. So essentially there are some conditions, because it's not so trivial. So maybe in the constant coefficients case can be easier, I don't know, but there is a result about the hyperellipticity. So just to...
Because constant coefficients on Rn, this would be, if you think of groups, this would be variable coefficients, but there will be constant coefficients with respect to some group structures. That's why we can calculate the symbol. This could give some interaction, but maybe we can discuss.
But then you see the zero set should have some kind. Say that the zero set has a group structure also. So it's a kind of because then you may have something which has a subgroup structure or not. So in a sense, if f is going to determine something which is a subgroup or not, well, this is going to give some differences, I think.
But you will see conditions, because it will be f and its derivatives, and they should interact, and you can see
I think so.
Conditions from symbolic assumptions.
Okay, so I think we have to stop here because we have another speaker waiting. So thank you again.